the woman who fixed Einstein's biggest mistake. The year is 1915. In the heart of a world embroiled in the chaos of war, a single mind, Albert Einstein, offers humanity a vision of the cosmos so profound, so complete, that it will forever alter our place within it. He presents to the world what can only be described as a masterpiece. This is not a minor correction to the old way of thinking. It is a total overthrow of a scientific dynasty. For more than 200 years, the universe has belonged to Sir Isaac Newton. His laws were supreme, his vision of gravity unquestioned. But now, a new theory of gravity, a theory of breathtaking elegance and revolutionary power, is poised to take the throne. Einstein gives it a name that will echo through the century: the theory of general relativity. Through a series of lectures, he paints a picture of reality utterly alien to anything that came before. The universe, he explains, is not an empty stage on which the drama of physics merely plays out. The stage itself is an actor. He describes a four-dimensional fabric, a seamless weave of space and time. Space-time, this is no static backdrop. It is dynamic, alive, a cosmic ocean that can be warped and curved, stretched and compressed by the presence of mass and energy. This radical conception of our universe is still celebrated as one of the greatest achievements of the human mind. It is a monument of pure thought. And yet, even a masterpiece can have a flaw. Even the most perfect-seeming theory can hide, deep within its equations, a subtle and unsettling problem. Buried inside the beautiful mathematics of general relativity lies a contradiction, a perplexing inconsistency that threatens its integrity, its claim to be a true description of the universe. The theory, so powerful in its predictions, appears to falter when confronted with one of the most sacred laws in physics: the conservation of energy. Energy, we believe, cannot be conjured from nothing, nor can it vanish without a trace. It can only change form. This is not a trivial concern. This is not a small, numerical glitch that can be patched and forgotten. It is a profound puzzle that strikes at the heart of Einstein's universe. Einstein himself, for all his genius, wrestles with it. He cannot fully resolve it. The issue is so confusing, so entangled, that the greatest physicists and mathematicians in Europe find themselves utterly unable to arrive at a clean, satisfying solution. The answer will not come from a famous professor at a grand institution. It will come from a woman the world is actively trying to ignore, a revolutionary thinker who is not permitted to hold a formal job, who receives no pay for her work, whose lectures must be listed under a man's name as a matter of policy. This is the story of Emmy Noether, and how her profound insight into the nature of reality not only clarifies and saves Einstein's theory, but becomes an indispensable cornerstone of all modern physics, the monument and the crack. To grasp the scale of the puzzle, we must first stand in awe of the structure Einstein built. Before 1915, our understanding of gravity was purely Newtonian. For centuries, gravity was seen as a force, an invisible rope stretching across empty space, pulling objects toward each other across an unchanging stage. The universe was a clockwork, and gravity was one of its gears. Einstein saw something completely different. He imagined that space and time were not separate, and not merely a background. He saw them as woven together into a single, dynamic entity: space-time. In this new picture, gravity is not a force at all. A massive object like the sun does not pull the Earth through space. Instead, The sun's mass warps space-time around it, creating a curved valley in the cosmic landscape. The Earth, in its orbit, simply follows the straightest path it can through this curved geometry. It was a staggering reconceptualization of the cosmos. The equations that described it were beautiful. The predictions were profound, from the bending of starlight near the sun to the existence of gravitational waves, ripples in the fabric of space-time itself. But almost as soon as this magnificent structure is unveiled, a crack appears. That crack is centered on energy. The law of conservation of energy is perhaps the most fundamental principle in all physics. It is the universe's ultimate accounting rule. Energy can change form, from chemical to electrical, from motion to heat. But the total amount in a closed system must remain constant. In Newton's universe, energy accounting is simple. You have kinetic energy and potential energy. As a planet moves closer to the sun, its potential energy decreases, and its kinetic energy increases by exactly the same amount. The total stays constant. Einstein's theory blows this simple picture apart. In general relativity, space-time is not fixed. It is an active participant. The gravitational field is dynamic. It stretches, compresses, ripples, and carries energy across the cosmos. This creates a paradox. How do you properly account for the energy in a gravitational field? The field itself contains energy, but that energy, in turn, curves space-time. The equations begin to loop back on themselves. Einstein, Hilbert, and others discover something disturbing. When they try to write down a single, coherent expression for the total energy of a system in general relativity, the answer depends on the coordinates they use. Change your description, and the total energy changes. It's as if the amount of energy in the universe depends on your point of view. That makes no physical sense. Hilbert calls it the failure of the energy theorem. Einstein proposes a mathematical object called a pseudo-tensor to describe energy, but it's clumsy and unsatisfying. Everyone involved understands that this isn't the elegant solution the theory deserves. Physics has hit a wall. The brightest minds are stuck. They need a new idea, a new way of seeing, and to find it, they must turn to someone they've systematically excluded from their ranks. The world that never wanted. Her Emmy Noether was born in 1882 in Erlangen, Germany. Her father, Max Noether, was a respected mathematician, known for his work in algebraic geometry. Their home was filled with chalkboards, visiting scholars, and long conversations about equations and proofs. But no one imagined that Emmy would follow this path. As a girl, she was expected to learn piano, cook, sew, and prepare for the life set out for her: marriage, motherhood, domestic quiet. The doors of academia were barred before she could even approach them. German universities did not allow women to study mathematics in any formal way. Still, Emmy felt a pull she could not ignore. Numbers fascinated her. Patterns came easily. She saw structure everywhere, in language, in puzzles, in the world, but she kept this mostly to herself. No one had raised her to imagine a life in mathematics. She simply couldn't turn away from it. Her early teachers described her as gentle, polite, and exceptionally bright, but not destined for scholarship. The expectations were clear, the path predetermined, and yet, somewhere deep within her, a quiet spark waited. A spark no rule, no tradition, no barrier could extinguish. By her late teens, Emmy wanted something forbidden. She wanted to sit in lecture halls and study mathematics officially. But regulations were strict. Women could attend classes only if each professor personally granted permission, and even then they could only audit. No exams, no credit, no degree. Emmy did it anyway. She approached each professor with humility and determination. She knocked on doors asking to sit in, even though her name would never appear on a register. Surprisingly, many said yes. She sat quietly at the back, taking notes as fast as she could, absorbing ideas at a pace few could match. She wasn't allowed to enroll, but she learned everything. For years she studied this way, unofficial, unnoticed, unpaid. Then in 1900, a small opportunity appeared. Women were allowed with special permission to take the Abitur exam, a prerequisite for university-level study. Emmy applied. She was permitted. She passed. Brilliantly. Now she could petition to pursue a doctorate. Again, there were debates. Was it appropriate for a woman to hold a PhD? Many professors said no. Emmy persisted. Eventually, her petition was accepted. She wrote a thesis so original and well-structured that her examiners were stunned. They told colleagues privately, "She has a talent unlike any we have ever seen." And yet, upon receiving her doctorate, the university offered her nothing. No salary, no position, no office, not even a desk. She returned home to work under her father, unpaid, uncredited, and unacknowledged. Mathematics had become her life, but the world still refused to see her. Göttingen, the forbidden genius. In 1915, the winds of fate shifted. David Hilbert, one of the most prominent mathematicians of the century, wanted to bring Emmy to Göttingen University. He and Felix Klein believed that her mind could help solve deep problems in relativity and algebra. They were right. The faculty disagreed. In a heated meeting, the all-male faculty argued that appointing a woman would be improper, dangerous, and disruptive. Some warned that students would lose respect for a female lecturer. Others claimed women simply could not withstand the intellectual strain. Emmy wasn't in the room, but her presence loomed over the debate. Finally, Hilbert lost his patience. "Gentlemen," he said, "I do not see why the sex of a candidate should matter in the least. This is a university, not a bathhouse." His words echoed. They did not win. The faculty voted against giving her a paid or official position. Hilbert refused to give up. He did what he could. He listed himself as the instructor for advanced courses, and then quietly allowed Emmy Noether to teach them. Students who came to hear Professor Hilbert soon discovered that the true lecturer, the one with chalk on her sleeves and fire in her eyes, was Emmy. Though unofficial and unpaid, her reputation began to spread. She had the ability to illuminate mathematics like no one else, one student recalled. She thought faster than we could write. Her lecture rooms were filled with admiration. The faculty corridors were still filled with dismissal. For Emmy Noether, brilliance was not enough. The world still would not let her in. Throughout the 1910s and early 1920s, Emmy lived in quiet, constant financial struggle. She was in her 30s, yet had no official job and no steady income. She stayed with friends, shared simple meals with students, and lived in modest rented rooms. She spent her days writing papers, solving problems, and mentoring young mathematicians. Her name rarely appeared in official records. When she published, it was often with male colleagues who received most of the credit. Not because she lacked confidence, but because the system made it almost impossible for her to publish under her own name. during World War I, things grew even harder. Resources were scarce, funding dried up. Many mathematicians were drafted or displaced. Emmy stepped in, teaching more classes informally, filling in for absent colleagues, supporting students, all without pay. She never complained. She cared nothing for fame or prestige, one student wrote. Her joy, her pleasure, her life was mathematics. Her brilliance grew. Her network expanded. Her influence deepened. Society still refused to recognize the magnitude of her contributions. A spark ignites in Göttingen. Despite working in the shadows, Emmy gradually built an intellectual community around her. Students gravitated to her not because she had power, she didn't, but because she had something rarer, an astonishing mind and a genuine love for ideas. They began calling themselves Die Noether Knaben, the Noether Boys. They met in her classroom, in her small apartment, in cafes. They worked through problems, debated theories, argued and laughed. She inspired them not with authority, but with passion. Her lectures were chaotic and beautiful. She would start a complex equation, erase part of it, rewrite it in a new way, then leap several steps ahead, expecting her students to follow. They often struggled, but they loved it. To watch her think was to see ideas come alive, one student said. She did not lecture, another wrote. She discovered, and invited us to witness the discovery. Her mind was expansive, her insight razor sharp. Even advanced students were humbled, yet she treated everyone with warmth and patience. Her laugh was loud, her energy boundless, her curiosity infinite. By the early 1920s, Emmy attracted some of the brightest young mathematicians in Europe, many of whom would later shape algebra, topology, and theoretical physics. She was becoming a legend, quietly, unofficially. But still, the world outside looked away. In 1922, after years of pressure, the university finally yielded a little. Emmy was granted a small, temporary position at Göttingen. It was not a full professorship. It came with severe limitations, but it came with something she had never had before, a salary. It wasn't much. For the first time in her life, Emmy Noether was paid to do mathematics. The mid-1920s became her golden era. She produced some of her most influential work in abstract algebra. She wrote papers that redefined entire fields. She mentored students who would themselves become giants. Outside, politics darkened, Germany struggled, but inside the lecture halls of Göttingen, a new era of mathematics was unfolding, and Emmy Noether stood at its center. She had built a life through sheer force of intellect. She had carved out a place no one wanted to give her. She had begun to receive some of the recognition she deserved. The calm would not last. A storm was coming, a storm that would tear her world apart. The hidden language of the universe. For centuries, physicists accepted conservation laws as unquestioned truths. Energy is conserved, momentum is conserved, angular momentum is conserved. These were treated almost like axioms, empirical facts the universe seemed to honor for reasons unknown. Emmy Noether did not see them as starting points. She saw them as clues. Why should energy be conserved? Why should momentum remain constant? Why should rotational motion carry a conserved quantity? If these laws held everywhere, always, there had to be a deeper reason. Slowly she saw it. The universe was not enforcing conservation arbitrarily. It was following a hidden architecture. Symmetry. Not symmetry as we see in faces or snowflakes, but mathematical symmetry. abstract invariance in the laws of nature. If a system behaves the same, no matter when you look at it, that is a symmetry in time, and something must be conserved. If a system behaves the same no matter where it is, that is a symmetry in space, and something must be conserved. If a system behaves the same when rotated, that is a symmetry in orientation, and something must be conserved. The universe, she realized, is not governed by a list of separate laws. It is governed by invariance, by the ways reality refuses to change. The more she examined this idea, the more everything aligned. Patterns revealed themselves. Equations began to speak. Beneath every law she found purpose. What others treated as coincidences, she saw as inevitabilities. Physics was not a pile of disconnected rules. It was a cathedral, symmetrical, balanced, and she had found the blueprint. The struggle of Einstein's theory. To see the importance of Noether's breakthrough, we return to Einstein's crisis. General relativity is beautiful, elegant, and revolutionary. But hidden inside it is a mathematical issue so severe it appears to threaten the theory itself. Energy does not seem to be conserved. In Newtonian physics, energy conservation is automatic. But in a curved space-time, where distances stretch and bend, old notions fail. Energy appears to fade in and out of existence depending on the geometry. Einstein tries to fix it. So do Hilbert, Klein, Levi-Civita. They rewrite equations, adjust tensors, modify curvature terms. Every solution breaks something else. Every fix creates a new flaw. They are trapped inside their assumptions. They believe energy must be conserved, as it always has been. Yet their equations refuse to cooperate. They never question the deeper structure beneath that belief. Emmy does. From the moment she studies Einstein's equations, she sees them differently. Where others see chaos, she sees symmetry. Where others see a failure, she sees a misunderstanding. Energy is conserved in general relativity, but not in the old, simple way. In Einstein's universe, conservation emerges from the symmetry of space-time itself. When space-time respects a certain invariance, diffeomorphism, symmetry, the conservation laws arise naturally. Einstein had never viewed his theory through this lens. It was too abstract, too mathematical, too radical. Noether understood it instantly. She was not just patching equations. She was uncovering the principle beneath them. Noether's first theorem. In 1918, Emmy published the paper that would define her legacy, Invariante Variations Problemae, Invariant Variational Problems. On the surface, it looked modest. No grand pronouncements, just careful, precise mathematics. Within it, she delivered one of the most important insights in scientific history. Every continuous symmetry of a physical system corresponds to a conserved quantity. This is now known as Noether's first theorem. If the laws of physics are unchanged under shifts in time, energy is conserved. If they are unchanged under shifts in space, momentum is conserved. If they are unchanged under rotations, angular momentum is conserved. This wasn't a guess, or a pattern, or a conjecture. It was a theorem, mathematically rigorous and unassailable. Conservation laws were not separate facts. They were not mysteries. They were not accidents. They were consequences. Physics was no longer just a list of laws. It became a tapestry of symmetries, woven together by Noether's understanding. Einstein read her paper and immediately recognized its importance. Noether's theorem has captivated me, he wrote. It shows the deep interconnection of all conservation laws with symmetry. Even he did not yet see the full scope. No one did. Noether's second theorem. Hidden in the same paper was a second theorem, more abstract, but just as significant. While the first theorem deals with global symmetries, like shifting time or rotating space, the second deals with local symmetries, which can vary from point to point. These symmetries are the foundation of modern field theories. Maxwell's equations, Noether's second theorem, electromagnetism, Noether's second theorem, the electroweak force, quantum chromodynamics, general relativity, gauge symmetry, the Higgs mechanism, all rooted in the mathematics she laid down. This second theorem doesn't just relate symmetry to conservation. It ties symmetry to the very form of physical laws, dictating how fields interact, how forces emerge, how space-time curves. The entire mathematical structure of the Standard Model stands on the foundation she poured. It is no exaggeration to say that all of modern theoretical physics is, in a sense, a long elaboration of Noether's theorems. The theorem reaches Einstein. When Einstein fully grasped what Noether had done, he reacted with awe. "Miss Noether has penetrated to the heart of the matter," he wrote. "Her work stands on equal footing with the greatest discoveries in physics." He became her advocate, praising her openly in letters and conversations. Yet, while Einstein celebrated her privately, German universities still ignored her publicly. She remained without a full professorship, without a secure position, without the recognition her work so clearly deserved. Her theorems fixed the very foundation of Einstein's great theory, and yet she still had to fight for every inch of academic ground. The most powerful mathematical tool physicists had ever seen had been created by someone they refused to hire. Why Noether's theorem matters more than ever. At the time, physicists valued Noether's work because it resolved Einstein's energy crisis. But as the decades passed, the true significance of her theorems unfolded. With the rise of quantum mechanics in the 1920s and 30s, physicists realized that every conservation law in quantum theory flowed from Noether's framework. When quantum field theory emerged, her role became central. Gauge theories, the mathematical backbone of particle physics, turned out to be direct expressions of Noether's second theorem. In the 1960s and 70s, the electroweak theory, the discovery of quarks, the development of quantum chromodynamics, the unification of forces, all rested on symmetry and conservation in the Noether sense. In the 1980s and 90s, string theorists realized that even their most exotic symmetries were governed by the same logic. Today, when physicists search for dark matter, dark energy, supersymmetry, quantum gravity, extra dimensions, new particles, and new invariances of the universe, they use Noether's principles as their compass. Her work didn't merely fix a single problem, it transformed physics into a science of symmetry. She built the scaffolding on which all later theories could grow. And still, outside the world of specialists, her name is scarcely known. The weight of genius. By the early 1930s, Emmy Noether was quietly regarded by many leading mathematicians as one of the greatest minds of her time. Students crossed borders to study under her. Researchers sought her guidance. Her ideas influenced fields she had never formally entered. Yet she remained largely invisible in the official structures of academia. Her brilliance was undeniable. Her identity was inconvenient. She was a woman. She was Jewish. She was outside the system. Her theorems were changing everything. The world refused to change for her. She had solved what Einstein could not. She had unified physics at a fundamental level. She had reshaped mathematics itself. And still she lived modestly, quietly, with chalk, paper, and a mind that rivaled the greatest who ever lived. The storm that would come next would not care about her genius. It would not care about her contributions. It would not care about the universe she had revealed. History was about to tear her life apart, solving the unsolvable. Armed with her profound new understanding of symmetry and conservation, Emmy turned back to the problem that had drawn her into Einstein's world: the strange behavior of energy in general relativity. The problem again was that in a curved, evolving space-time, you could not define a single, fixed total energy for the universe. The quantities physicists tried to define seemed to depend on the coordinates used. The energy moved when the description changed. Einstein and Hilbert were obsessed with the missing energy. They asked, where did it go? Noether asked a different question. What is the symmetry? From her theorem, she knew that conservation of energy must arise from time translation symmetry. The idea that the laws of physics do not change over time. But in general relativity, space-time itself evolves. What does the same over time even mean when the stage is shifting under your feet? This was the crux of the issue. In her second theorem, she had already dealt with local symmetries, gauge symmetries that vary from point to point. General relativity is built on exactly this kind of symmetry. Noether proved that the odd behavior of energy in general relativity is not a bug. It is a feature. The failure of the energy theorem, as Hilbert called it, is not a breakdown. It is a direct, unavoidable consequence of the symmetries at the core of Einstein's theory. She showed that the energy of matter and the energy of gravity are so deeply intertwined that trying to separate them into neat, global totals is fundamentally misguided. Locally, in a small region of space-time, energy is conserved exactly as expected. The local accounting works. But on cosmic scales, where space-time itself stretches and evolves, the bookkeeping becomes subtler. For example, as light travels to us from distant galaxies, its wavelength is stretched by the expansion of the universe. The light becomes redder. It loses energy. At first glance, energy appears to vanish. But in Noether's framework, this loss is not a violation of a sacred rule. It is a reflection of the fact that the universe is not globally symmetric in time. The stage is changing. She did not patch Einstein's theory. She showed that the supposed whole was never a whole at all. She provided the language needed to speak sensibly about energy in curved space-time. She resolved the paradox that had stumped the greatest minds of her time. Einstein was stunned. In a letter to Hilbert, he wrote in admiration of Noether's work, remarking how impressive it was that such general and abstract things could be grasped so clearly, and suggesting that the old guard might do well to learn from her. The woman not allowed to have her own name on a course catalogue had provided the bedrock for his revolution. What others had seen as a crack in the monument, she revealed as a supporting beam. The cornerstone of everything, solving the energy puzzle in general relativity alone would have secured Emmy Noether's place in history. But her theorem did more than that. It gave physicists a universal key, a master tool to unlock the structure of any physical theory. In the decades that followed, as scientists probed deeper into the atom and developed quantum field theory, they realized something extraordinary. the most powerful way to describe the universe was not by listing particles and forces, but by identifying its symmetries. The entire standard model of particle physics, our best description of the fundamental building blocks of nature, is built on the foundation of Noether's ideas. Physicists no longer simply guess at forces. Instead, they propose a mathematical symmetry, then use Noether's logic to see what conservation laws, what forces, and what particles must appear as a consequence. Take electric charge. Physicists noticed that in all observed interactions, the total electric charge is always conserved. Using Noether's logic, they asked, what symmetry enforces this? They found it, an abstract symmetry in the quantum fields of charged particles. Insisting that the laws of physics respect this symmetry makes the electromagnetic force and the photon mathematically inevitable. The symmetry dictates the force. The same is true for the strong nuclear force, which binds protons and neutrons, and the weak nuclear force, which govern certain radioactive decays. Each is the manifestation of a deep symmetry, described by abstract groups like SU3 and SU2. The intricate ballet of particles that make up reality is, in a sense, a dance choreographed by symmetries. Symmetries that Noether taught us how to read. Her work has become so ingrained in the way physicists think that many use it instinctively, like a craftsman using a familiar tool. It is that fundamental. She transformed physics from a discipline that catalogued laws into one that seeks symmetries. Find a new symmetry in nature, her work tells us, and you may uncover a new conservation law, or even a new force of nature. Years after her death, Einstein wrote a tribute to her in the New York Times. In the judgment of the most competent living mathematicians, Fräulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began. Even that sounds almost modest now. Emmy Noether was not simply a great female mathematician. She was one of the greatest mathematicians of the 20th century. Full stop. And the theorem she forged under the weight of prejudice and exclusion is one of the most essential and beautiful pillars of modern physics. A life of principle. After her monumental work on symmetry and conservation, Göttingen belatedly relented. In 1919, after the upheaval of World War I, Emmy Noether was finally granted the right to teach under her own name, her habilitation. In 1922, she received the official title of Associate Professor, still without proper pay, and still far below what her contributions warranted. For the next decade, Göttingen was her kingdom. She was not a conventional teacher. Her lectures were spontaneous and informal. She mumbled to herself, paced in front of the blackboard, covered her simple dress in chalk. But for those who could follow, the experience was electrifying. She was warm and nurturing to her inner circle. She hosted mathematical walks through the countryside, discussing algebra for hours. Her devoted group of students, the Noether boys, absorbed not only her ideas, but her spirit. During this period, she revolutionized abstract algebra. Concepts such as Noetherian rings and Noetherian modules are now standard, taught to graduate students around the world. In 1932, she was invited to give a plenary lecture at the International Congress of Mathematicians in Zurich, one of the highest honors in the field. Her long overdue recognition had finally begun. Then, as quickly as it came, it was taken away. In 1933, the Nazi Party seized power in Germany. As a Jew, a pacifist, and an intellectual, Emmy Noether became an immediate target. She was among the first professors dismissed under the new laws. Her colleagues scrambled to help. Einstein, already in exile in Princeton, advocated for her. She soon found a new home at Bryn Mawr College in Pennsylvania, a women's college, and began lecturing at the Institute for Advanced Study. In America, she found a community that finally welcomed her without reservation. By all accounts, she was happy. Her time there was tragically short. In 1935, doctors discovered a tumor. She underwent surgery. Initially, it seemed successful. Then a sudden post-operative infection struck. She died at the age of 53. Her death stunned the scientific world. She was at the height of her powers, and then, in an instant, she was gone. If you've learned something new so far, if Emmy Noether's story has surprised you, take a moment to like this video, and don't forget to subscribe. The history of science is full of stories like hers, stories of brilliant minds who changed our understanding of reality, yet whose names are not widely known. Many of them fought systems that tried to silence or sideline them. Many never saw the full impact of their work. If you believe these stories deserve to be told, if you want to meet more of the forgotten minds who shaped our modern world, consider subscribing to this channel. Your support helps bring these lives out of the shadows and into the light. The twofold legacy. Emmy Noether's legacy is twofold. First, there is the legacy of her work. She gave physics a new language. The idea that symmetry is the ultimate guiding principle of the universe flows directly from her insight. Her theorem is not a historical curiosity. It is a living tool, used every day by physicists probing the deepest questions of the cosmos. In its own way, it is as fundamental as E/mc2. Second, there is the legacy of her life. It is a story of resilience in the face of exclusion. A story of a woman pursuing her passion with joy and dedication despite poverty, sexism, and institutional indifference. When we think of the giants of physics, we often think of Einstein, Newton, and Maxwell. We should also think of Noether, the woman who worked for years without pay. The woman who was forced to lecture under a man's name. The woman whose mind saw a truth so deep and so powerful that it clarified a critical puzzle in Einstein's revolution and laid the foundation for almost everything that followed in fundamental physics. Her story is a reminder that genius knows no gender, race, or religion, and that sometimes the most revolutionary ideas come from the very voices the world tries hardest to silence. Thanks for watching. If you love stories about the scientists who changed our world, don't forget to subscribe and stay curious.